So sorry about kind of the craziness of last week. I almost came in Wednesday. Wasn't feeling terrible when I woke up, but I figured you better be safe than sorry, and I guess I made the right decision. So I put up that recording on Friday, which was pretty much me working through the rest of frequency distributions or histograms in Excel. So I kind of expect that all of you go kind of watch that. It really was kind of similar to what we had done in class on that Friday, the previous Friday, but it was just kind of doing shorter bins. I also showed you how to kind of insert some graphs, scatter plots, time series graphs. So I kind of went over, everything in that video. It'll be really helpful when you're tackling the first Excel assignment, which you can see up on Canvas now. So that's due next Friday. You should be able to work pretty much through all of this. I think there's some maybe stuff that we'll talk about on Wednesday, kind of some real basic calculating means and variances. It's pretty easy to do in Excel, and we won't have really gone over that until after Wednesday, but you should be able to get 80–90% of that Excel assignment done based off of what we've done in class, as well as that additional video I posted Friday. Okay, so those are good resources to go back and be able to watch. They're up there on the YouTube playlist. You can always kind of go back and rewatch them. I also put up under that in-class data folder. So we were working off a blank version of the file and kind of build it together in class, and then the additional video, I kind of worked through the rest of it. The completed version, that complete version of the Excel file is also up there on Canvas, so you can go and kind of look at how it should have been done, like how everything I worked through. It's all in that file, so that's a really good template for that first Excel assignment. Okay, so using that file as well as kind of those videos will probably be helpful as you're going through that. But if you have any questions anytime, feel free to reach out. And if you're getting stuck in something in Excel, especially with that count ifs formula, sometimes it's just a small syntax thing. So I mentioned in that recording, you should be using the count ifs formula. If you Google histogram, there is like a built-in tool. You won't get full credit for using that. I don't want you to use that. It's also very difficult to use when you kind of create these catch-all categories and kind of unique bins. If it's anything other than that optimal bin length, it's very difficult to use. I want you to get used to using these count ifs formulas. Part of the grading for that Excel assignment is doing the work, showing the work in Excel, and part of that is using that count ifs formula to get your frequencies. Okay. I also put up the first Connect assignment. You should be able to get through probably 7 or 8 questions, which I think there's 15 based off what we've already done. After today and Wednesday, you should be able to get through kind of all of them. Yeah, honestly, some of it, even after, even before today's class, might be some knowledge some of you have had. We'll talk about things like means or averages. So some of that's in there. That might be stuff you could have actually already worked on as well. Also, before we get into it, there was on the online quiz, there was one small typo, so I'll probably end up giving everybody credit for the last question. I think I meant to say cumulative relative frequency. And all I said was cumulative frequency. We'll discuss at the very end. I'll kind of review cumulative frequencies a little bit for us if we have enough time. And I think it'll may make sense why that question was incomplete. And I'll describe that a little more in detail. Okay. Other questions for me moving forward? So hopefully, if what they say is true, hopefully we'll be fine for the rest of the semester. At least I'll be fine moving forward. We shouldn't have to do this again. But I appreciate your kind of patience with everything last week. So these slides kind of, I guess, I just want to make sure they're on there. They're also a good kind of source to go back and look at. These are all things that I talked about in that video I posted, kind of cumulative frequencies, how to put a scatter plot in, what the scatter plot would look like. I think I used different data in the video. And then we're doing time series graphs as well. So these are just more like kind of, bullet point kind of steps into how to do that. If you go back and watch the video, I kind of go through those, or I said them out loud, but here's kind of them written down. So if you're kind of working on an Excel assignment, these slides might also be helpful. But this is all stuff that I covered in that video. What I didn't get to, and what we'll talk about today, are going to be, we've got these frequency distributions or these histograms, and they tell us something about the data, right? Visually, we can see, okay, this is the most frequent kind of observation for this variable. Here's some that aren't as likely. And we can start to think about distributions of a bunch of different types of variables, right? But we also want to have different measures, right? Even though I'm looking at this distribution, it's kind of hard to see like, well, where's like the average, or where's the middle part of this, right? So we want to come up with statistics that tell us more about the data than just the visualization of their frequency distribution. So a couple different types of distributions we'll see, and then we'll kind of relate this to some statistics that we'll talk about today, which are measures of central tendency. So the first kind of example here, or one that'll pop up a lot, is if I were to draw a line through like the top of each one of these bars, or something that kind of best fit this distribution, it would kind of look like this nice bell shape, right? So we'll call this a normal distribution, and we'll really dive into it after the first exam, right? In terms of some more of its properties and how we can exploit it. I shouldn't say exploit, how we can use it to our benefit. So, a normal distribution, nothing's going to be perfect, right? Obviously, there's like some dips here in some of these categories, but pretty close, this nice bell-shaped curve that if I were to fold it in half, right, it would almost exactly fold on top of itself, or we would say it's symmetric, right? So if we have a symmetric distribution, that would be kind of our nice normal distribution. It looks like, kind of a bell curve here. We might also see data that looks like this. So if I had like income data, and here they did a histogram, it's broken up into $5,000 bin lengths, except for once they get up to these high categories, this is what? 200 to 250,000 or over 250. So they have these catch-all categories at the end. Because if you were to continue to do $5,000 increments all the way up to whatever Jeff Bezos is making, right? Probably shouldn't, or Elon Musk, whoever, choose your billionaire. I would just have this extremely long right tail, right? So if I have this extremely long right tail to my distribution, we would call that a right skewed distribution. Now that's visually how we can remember. By the end of the class today, I'll tell you exactly why we call it right skewed. But for now, you can just think about long right tail, you get this right skewed distribution. On the opposite end, right, I might have a long left tail. That would be a left skewed distribution. So example of this would be something like the length of a pregnancy. So gestation or length of pregnancy. Most pregnancies are 38, 39, or 40 weeks. However, there's a lot of premature births as well. So we have kind of this long left tail, but we aren't seeing babies born at like 12 months, right? We don't have this right tail that exists for the data. So long left tail, this is left skewed data or left skewed distribution. And then maybe I have something like this. So I think here I've got like basically weight, body mass. So it looks like here I've almost got like two normal distributions going on. So what might be going on with this data? I'm looking at weight. Why might I have two normal distributions? Yeah, right. So I know that maybe if I see something that looks like it's bimodal, I should probably be thinking about whatever the variable I'm looking at is. There's probably a characteristic. There's almost like two groups in my data set, right? So you can think about if I were to look at kind of female weight and say, think about kind of where the middle of that distribution is, or where's the average. And we'll talk about average here in just a second. But maybe the average of the data is somewhere here, and here's this nice kind of normal distribution. And then I think about if I had my male data in a different data set, and I were then to plot that distribution, they're both going to look normally distributed, not female, right? The male data is going to have a slightly higher mean or higher average. Right? We'll talk about means here in a second. I didn't mean to use that terminology yet. But the interesting thing about when we're thinking about distributions, yeah, the averages of these two groups might be different, but this is why it's good to also think about the distribution around that average, because if we take any one person, right, any one female, well, their body mass could potentially be greater than any one male, right? There's males over here who have weights lower than females over here, right? So there's overlap in these distributions. If we look at any one observation, yeah, any female weight could be greater than male weight or vice versa. It's just that if we're thinking about comparing the two groups based off of their average, right, this male distribution is shifted a little bit to the right. Okay? So, but if we throw them all together, we have what we call a bimodal distribution. Probably a good indicator. We might want to separate this out, separate these this data set up based off of some characteristic. Right? maybe if I had like income data, but 2 different countries, right? Maybe there I would have 2 distributions, but right, if it's a third world country, they're going to have a lower average income than kind of a first world country. Okay. Any questions on this before we keep moving? Shouldn't be anything too crazy yet. Okay. So we've got these distributions, but we want to know more about them, right? So we want to calculate other statistics that tell us something about the data. So if I can get my slides to work, there we go. So the first thing we're going to do is we're going to try to come up with measures of central tendency, or where's the middle part of this data set, right? So the 3 measures we have, and here I'm going to kind of start introducing you some notation today. We'll start writing things out mathematically, are the mean, the median, and the mode, okay? So when we write out these statistics, if we're dealing with population data, we typically write things out with Greek lettering. So here mu, right, this mean, represents the population mean. So mu here, this Greek letter, represents our population mean. If we're using kind of our standard English lettering, right, and usually we either use like a bar or a caret to denote that this is a sample statistic. So X bar is our sample mean. Okay, mu is our population mean, X bar is our sample mean. Our median and our mode don't quite fit this convention. We typically just write them with a capital M subscript D for median, capital M subscript O for mode. If you really want to be complete here, the capital M's represent population means and mode, or sorry, not means, population medians and modes. If we want to be real complete, the sample median and mode would just be the same thing, but using lowercase lettering. I'm never going to try to trip you up with that, or you're not going to be necessarily have to type that in anywhere. But to be complete, right, if we wanted to distinguish between the sample and population data for our median and our modes, we'll use just capital or lowercase lettering. But more conventionally, like everything else we'll do in this class, Greek lettering is the population, and then kind of English lettering will be our sample statistics. Okay. Now, there's no difference in how we calculate them. I'll kind of show you the formula here in a second. There's a little bit of a difference in the notation, but the procedure would be the same to calculate both a population or a sample mean. Okay. And then next class on Wednesday, we'll dive more into detail into this. We're going to be looking at measures of variation, and they follow kind of the same sort of procedure. So I've got my variance and my standard deviation. So the variance, right, from a population data set will be sigma squared. But if it's a variance from our sample data set, it's just we're going to notate it with S squared. Kind of, lets people know this is coming from a population or a sample data set. And then the standard deviation is just like we're scaling the variance, so we just take the square root. So that would be sigma is our population standard deviation, S is our sample standard deviation. And there will be a slight difference in how we calculate these, and we'll talk about that on Wednesday. But for now, getting used to kind of that Greek lettering for the population and kind of our English lettering for the sample. Any questions so far? Okay. So how do we calculate these statistics, right? So today we'll talk about calculating measures of central tendency. So the first one is our mean, right? Either a population or a sample. So let's say, for a second, if I have 5 observations, how would you find the mean or the average of 5 observations? I've got 5 numbers. How do I find the average of those 5 numbers? Add them up and divide by 5. Or if I want to keep it general, no matter what number of numbers I have, I add them all up and I divide by the number of numbers in that data set, right? So that's what I'm going to be doing to find the average or the mean, right? We don't really want to necessarily call it the average. The mean is really the technical term we want to use, but it's the same thing, right? The mean or the average. So if I were to write this out mathematically, it's going to look like this, and I'll break this down for us, okay? So we already know how we calculate the average or the mean. We just said it, right? So this is the mathematical representation of that. So this capital sigma sign here, right, we'll call that our summation sign or a sum sign, right? And it's going to say, okay, start at the very first observation and go to capital N represents the total number of observation in a population data set. So start with the first observation and go to the very last observation and add up whatever is to the right of this summation sign. Well, what's to the right of this summation sign is just, x1 would be the value for this x variable that I see from the first observation. x2, the value for this x variable from the second observation, so on and so forth. So this summation sign just says, take the value for that x variable from the first observation, add to it the value for that x variable from the second observation, add to it the value for this x variable from the third, all the way to the very last one. Writing that out a little bit differently without a summation sign, you're just saying, take the value for this x variable in the first observation, add to it the value for that x variable from the second, all the way to the very last observation. Okay? So basically that numerator is just saying, take this variable x I want to find the average of or the mean of, add up all those values, right? And then divide by capital N, which is just the total number of observations I had in that data set. So add all these numbers up and divide by the number of numbers that I had. Right? So we're just writing it out mathematically. Okay? Now, the reason why I want to break this down a little bit, and I'll come back to this in just a second, is because I think it connects to some things we'll talk about moving forward. So here's my population mean written out kind of mathematically. The sample mean, I'm going to calculate the exact same way. There's just one slight difference, which is instead of capital N, I'm going to use lowercase n here. So lowercase n represents the total number of observations in my sample data. Capital N, number of observations in the population, lowercase n, number of observations in my sample. Okay, so lowercase n will always be smaller than capital N, right? My sample is always a small subset of the entire population. But in terms of calculating, right, I still just add up the number of, add up all the values for this x variable in my sample data set, and then I divide by the total number of observations I have in the data, which is no longer population, but it's now the number of observations from my sample. Okay? But procedurally, it's the exact same. Right? So, if I had a data set with every birth in the US, how would I find the mean birth weight? I just add up the birth weights of every single birth I had in the data, and then divide by the total number of births that I had in that data set. Right? And I think we'll use this data set a little bit throughout the semester. And I think it's 3,200 grams about. Okay. Any questions here with any of the notation? Kind of, I'll call this as capital sigma, but usually I just refer to it as the summation sign, right? And we'll kind of get. We'll use it throughout the semester. So if you have any questions at any point with any of the notation or math part of it, let me know. I'll usually say it in words, but you'll kind of visually, we'll see these formulas. Okay. Any questions up to this point? All right. So let's say I had an example, right? How would I find the mean for this data set? So I've got 7 games being played. I don't care what game it is, basketball, boggle, whatever it is, right? How would I find the mean points scored here? What would the first thing you would do is, if I had a calculator in front of me, what should I do?
Add up all the points.
Yeah, just add them up, right? So 20 plus 35 plus 15, all the way down for the very last observation, and then divide by the total number of observations I have, which is I've got 7 games. Easy to see in this small data set, right? So I add up all those values for the variable that I'm interested in finding the mean of, points scored, and then divide by the total number of observations that I have. Okay. Any questions? You probably calculate averages and means in other classes before, I would imagine. But I'll give you a slightly different way of thinking about the mean. This is because it's going to connect to what we're going to do on Friday. So let's say I said the one version of this we can kind of think about. So this is going to be our population mean, right? Add up all the values, every single observation, and then divide by the number of observations we had. I can rewrite this a slightly different way. So if I divide everything by the same number, I can kind of pull that n out and this is the exact same thing. Okay. One thing that we'll exploit a little in this class, or we'll see things written slightly different. If I'm dividing by a number, it's the same as multiplying by 1 over that number. So another way I could think about this is, I could write it out like this. And the reason why this is a useful, at least kind of thought experiment or way to look at the mean, is because really what we're doing with the mean is we're saying, okay, where's the middle part of the data? But every observation is carrying the exact same weight, or it has the exact same pull on that mean. Notice here, every observation is being weighted by 1 over the total number of observations. And that's because that observation represents 1 out of however many observations we have. So the mean inherently is like we're finding a weighted average, but it's just that every single observation carries the exact same amount of weight. Okay. Now I'll use this in a second to also make another point. So that's one way of thinking about this, right? Every observation is influencing the mean by exactly 1 over n, or 1 out of the total number of observations here. So if I had like this commute time, kind of show you, right? This is another example. I'm not going to spend too much time on this, but I want to show you something with this slightly different data. So here I've got my commute time. If I gave you a set of answers like this, which one of these could you rule out right away? So I want to find the mean commute time here. Why could you rule 15 out?
All the numbers on the list are greater than 15.
Yeah, so when we're calculating these statistics, and this really starts to apply more when the stats get harder to compute, don't get too lost in the formula or the math. I mean, we can make mistakes, right? And I want to be able to quickly identify mistakes. In fact, a lot of times with like the online quiz questions, or even sometimes on the exam questions, I'm more so like, look, we can all make computational errors, right? Like it's easy to hit the wrong button on a calculator, right? But we should be able to easily identify. I mean, most of the time we're going to have Excel or a computer program doing stuff for us to calculate these statistics. So we're not doing it all by hand, wasting time. But we need to be able to like know what that statistic is and know when like, oh, this answer, something must have went wrong. Right? Like we have to be like the last line of like troubleshooting for computers a lot of the time. So here, if I'm trying to find a measure of central tendency, which is the mean, it should be a value that's somewhere in the middle of the data. How can the middle part of the data be less than the minimum, right? So at the very least, my mean should be somewhere in between the minimum and the maximum, right? Somewhere in that range. So here, I've got a minimum of 20, maximum of 90. That mean should be somewhere in between those two values, right? So 15 doesn't make any sense. Okay? So start to think about not just like plug the numbers in, get it entered in my calculator. Like think about before you even start, which of these answers don't even make sense. I can rule one of these out right away. Okay. But we actually want to go through this, right? Just add up all these commute times, divide by the number of employees we have here, which is 7, right? And I get this mean of 45. Okay. So one thing I had said earlier was every observation is kind of carrying the same amount of weight here. So we can actually, I had someone ask this question last class. I think it's like a valuable, just to kind of look at it. It's interesting. So let's say I copy this here. Open another sheet. I'll zoom in so we can see what I'm doing. I'll paste those values in there. All right, so there's my commute times. Okay. Well, one function that I showed you the Friday that we met last was we had this sum function. It just adds up numbers for us. So here, if I add up all my commute times and I divide by the number of observations I had, which was 7 from that data set, this should give me the mean, right? I added up all the numbers, divided by the number of numbers I had. Another way of doing this is saying, if I were to divide every observation by n and then add them all up, I should get the exact same value. That should also give me the mean, right? So here, I could create another column, which is not 1, sorry. Take the value for x at 20, divide it by the total number of observations, right? And then do that for every single observation here, right? So when I copy that down, remember my cell references update. So I'm taking every value, dividing it by n. Well, now if I add these up, that should give me the exact same value, right? So that was, right, thinking about dividing every observation by n and then adding those up, kind of showing me that like everything is influencing the mean by 1 over n. I get the exact same value. Right? So there's different ways of kind of tackling the same thing. I think probably the first way is easier, just because you start dealing with a lot of like kind of nasty decimals here, and then what decimal number do I round to if I'm not doing this in Excel? But it's another way of thinking about the mean. So every observation is having the exact same influence over the mean, but then we start to run into a problem. Okay. So let's say I've got 2 data sets. 2, 4, 6, 8, and 10. Okay. If I calculate the mean here, I add all these up. So 10 plus 20, so 30 divided by the number of numbers I have, which is 5. So 30 over 5. My mean is 6. We'll assume this is population data. Now let's say I have another data set over here. And the first 4 observations are exactly the same. But the last observation is 100. Right? So what would the mean of this data set be? Well, first of all, relative to the mean of this data set, what should be true about the mean of this second data set? It's going to be greater, right? It has 4 of the exact same observations, but one of them is higher, so it's going to pull that mean up, right? It's going to add a larger value into that numerator or make that mean higher. Okay? So I add these up, I get what? 120 divided by the number of observations I have, which is 5. So this has a mean of 24. Okay? So with a small data set, we can start to see a problem with relying solely on the mean. What happened here was I have 2 data sets that are pretty similar other than 1 observation. But when I have a small data set, one extremely large or extremely low value can greatly influence the mean, right? And the problem is here, like if I use this mean, I only have 1 observation that's greater than the mean, but I have 4 that are less than it. So it's like, is this really a measure of central tendency? Because the vast majority of my data is far below this value. I just have 1 observation, right, that's pulling it up. So with really small data sets, each observation carries 1 over n weight. But with 5 observations, that's 1/5. Right? However, what if I had like 1,000 observations? Well, then this extremely large value is only going to be influencing the mean by 1 over 1,000. Right? So larger data sets, the mean is a lot more reliable. Like it's not as heavily influenced. But with small data sets, it can really influence the mean a lot. So then we need some other measures, right? So the second and third measures we'll talk about are the mode and the median. So the mode is really easy, right? This is just what value happens the most, or what's the most frequent value for this X variable, right? So if I was looking at like a frequency distribution, like let's say I had the number of kids in a household and I plotted all did the bar graph, how could I quickly identify what the mode is? It's the most frequent value I see for this variable. I'm looking at this bar graph, it's just going to be what? The highest bar, right? Whichever bar shows me this observation has the highest frequency. It happens the most often, okay? So it's pretty easy visually usually to identify the median. Right? The mode, it's easy to identify. The median is a little bit different, right? So this kind of fixes our problem with the mean. The median is going to be the value that exactly splits the data in half. So if I were to arrange the data from smallest to largest, the median is the value such that 50% of the observations are below that value and 50% of the observations are above that value. So if I had like 101 observations, I would look at whatever value is in that 51st position after like I arrange them from smallest to largest. Whatever value is in that 51st position, there would be 50 observations above it and 50 observations below it. So that would be my median. Okay. Now it's nice and easy with an odd number data set because there is going to be whatever, there's going to be a number exactly. But think about if I had, 7 observations, right? I arrange them from smallest to largest. If I take that value that's in the 4th position, there will be 3 observations below and 3 observations above. However, if I have a data set with 8 observations, I'm going to be left with 2 numbers in the middle. So if I have 2 numbers left in the middle from an even number data set, how do I find the median? Excuse me. I'll just take those last 2 numbers in the middle and find the average of them. So let's say, I arrange my data from smallest to largest. I find these 2 numbers in the middle of the data set, and let's say they're 10 and 12. Well, the median there would just be take the average of those 2 or 11. Right? Add them up, divide by 2. So 10 plus 12, 22 divided by 2 is 11. Okay. So a little bit more work if we have an even number data set, but not bad. Okay. Now we have some built-in functions in Excel that make this easy to do with big data sets, but we'll take a look at how we do this with small data sets. So here, if we use this point score data, what would be the mode? So this is going to be what happens the most frequent. This is kind of an easy with a small data set here. So I heard someone say it. The only observation that even happens more than once here is 35. So it will be the mode. Okay? Now, with small data sets, you can imagine we run into a problem sometimes, which is, let's say that game 6 was gone. Well, now there's no observations that happens more than once. So with a small data set, like it's kind of hard. You can't find the mode sometimes. It doesn't exist. Like everything only happens once. But with a really large data set, the mode becomes something that's a lot more useful, right? Or more relevant. Okay. What would the median be here? So the way I would find the median is I want the value that's exactly in the middle of the data. So I'm going to start crossing off the highest and the lowest, then the next highest, next lowest, until I'm left with one number in the middle here. So cross off the highest and the lowest values. Oops. Next highest and next lowest. Next highest, next lowest. And I'm left with a number that's exactly in the middle. So 20 here would be my median. Okay. Any questions on that procedure? So fairly easy with a small data set, right? You can imagine, let's say I use that commute time. And I had, gave you these options. Well, once again, can we rule any of these out? No, I mean, I'm looking at a measure of central tendency here with the median. It should be somewhere between 20 and 90. All these possible answers are. So unfortunately here, I can't rule anything out. Right? However, a nice trick with these small data sets, instead of because sometimes looking at this, I might get mixed up a little. If I write the observations out from smallest to largest, now it becomes a lot easier to see, okay, the number that's exactly in the middle, 40, there's 3 observations below it and 3 observations above it, right? Or I cross off the lowest, highest, next lowest, next highest, next lowest, next highest. I'm left with that value that's exactly in the middle of the data. So sometimes writing it out from smallest to largest makes it a little bit easier to find that median. Okay. Any questions? Okay. So let's go back to our old 2 data sets here. What would the median of these 2 data sets be? I'm left with 6 here. Then over here, cross off the lowest, highest, next lowest, next highest. Notice here, this one extremely large value, because with the median, it just depends on the number of observations on each side. It just gets crossed off. So it could be 10, 100, it could be 1,000. It doesn't influence the median at all, right? However, right, you can kind of see that really extremely large value greatly influence the mean, right? So with small data sets, sometimes you want to rely a little bit more on the median because the majority of this data set, right, is between 0 and 10, right? So 6 is probably a much better kind of measure of central, the center point of this data, and it's not influenced by this extremely large value, okay? Any questions here? I'm going to kind of connect this now to something we've already talked about. So we talked about skews of distribution at the beginning of class. Okay. Well, notice here, I've got a scenario where I have some extremely large values that pulled the mean up a lot or pulled it to the right. So anytime I have a median that's less than my mean, kind of writing out in words here, if the median is less than the mean, visually that means the median will be to the, visually that means the mean will be to the right of the median. So this is what we would call a right skewed distribution, right? We've got these extremely large values on the right side of the distribution that pull the mean up a lot, but don't influence the median. So anytime, even if you don't visually see the distribution, if you can calculate the mean and the median, if the mean is greater than, it would be to the right of the median, we would say we have a right skewed distribution. Okay. You can imagine if I had extremely low values, that would pull the mean below the median or to the left of the median, and we would say we have a left skewed distribution. So kind of here, this slide is kind of giving a nice visual of that. If we've got really extremely large values, like with the income data, like Elon Musk and them, they're going to pull the mean income up. I think I saw the other day, it's like 53,000 or something like that. But if we go back and look at this distribution, the majority of people are making far, like the highest bars are all well below $50,000. It's just that that mean is being pulled to the right by these extremely wealthy individuals. The median there is probably going to be a better representation of where like the income the majority of Americans could expect, right? So anytime the mean, there we go, is to the right of the median or greater than the median, we've got a right skewed distribution. That's really where the name comes from. Now, visually, it's easy to see, like if you have the distribution graphed out, long right tail, right skewed distribution. But the real naming of it comes from the fact that the mean is to the right of the median. And then the exact opposite is true for a left skewed distribution. If our mean is extremely low values, it pulls the mean down such that the mean is to the left of the median, we would say we've got a left skewed distribution. Okay. And then if it happens to be that the mean and the median are exactly the same, we would say we've got a symmetric distribution, right? You can kind of think about this data set we had here. Every number on either side is like equidistant from that mean. And so our mean ends up being exactly equal to the median. Okay. So that would be our symmetric distribution, or a normal distribution has that property as well. Okay. So that's more so where the naming comes from, right? That relationship between the mean and the median. Okay. So, something I might ask you on a homework is something like, based off the mean and the median, what skew does this variable have? And then you should know that, right? If the mean is to the right or greater than the median, it's right skewed. And then the opposite is true, right? If the mean is less than the median, we would say we have left skewed. Okay. Any questions there before we keep moving? A couple of things here before we get out. So on Wednesday, we'll kind of start going in more depth into measures of dispersion. I'll introduce one today and we'll identify its shortcoming, and then we'll kind of have a solution on Wednesday. So if I'm looking at a data set, I want to know not only where's the middle, where's the average, the mean, the median, what's like the variation? Because I could have two data sets with the exact same mean, but one of them, so think about it this way. Let's say I had an observation or a data set that ranged from like 1 to 10, right? I take the average, and the average or the mean is 5. But there's some variation to that data, right? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then I have another data set, it's 11 observations or whatever, but they're all, and so the average of that first data set was 5, right? The mean. The second data set also has a mean of 5, but every value in the data set is 5, right? So same mean, but there's like no variation in one of the data sets, more variation in the other. How do we capture that? Okay. So the first is going to just be finding the range, right? The difference between the minimum and the maximum value. So for example, this commute time data set, our range would be, well, the minimum's 20, the maximum's 90. So we have those two values, the difference between the two. There's just a range of 70 there. Right? So, something with a range of 70, there's a lot more values this variable could take on. There's a lot more variation in this data set than if I had a range of something like 5. Well, there I've got a pretty narrow window of where I'm seeing this X variable take values, or the values for this X variable. So one problem with this range is, let's think about 2 data sets here. So let's say I've got a data set where everything is 1, right? I guess maybe I'll write it like this. So, and then the very last observation is 100. Then I have another data set, 1, 2, 3, 4, all the way up to 100. Well, the range of this data set is 99, and the range of this data set is also 99. But there's a lot more variation in this data than there is here. These are all 1s and 100, or 1, 2, 3, 4, 5, 6, all the way up to, right? There's a lot more variation so we need another statistic that can capture that, because the range isn't doing that, right? So how do we do that? What statistic will we use? We'll end up calculating a thing called variance, and that'll allow us to identify the difference in variation between these 2 data sets. We'll do that on Wednesday. But one more thing I want to go through, kind of review. I went through it in that video, but I think I can do a better job and maybe kind of give a little more insight kind of today. So one of the things I did in Excel in that video is kind of show you how to calculate cumulative frequencies. Okay? So if we had a distribution, and here I'm going to be a little bit lazy for the sake of time with my equalities here. Obviously, I can only include one equality, so that 10's only counted in one of these bins. But let's say I had a frequency distribution and something like this. Okay? So I've got the frequency of each one of these bins, right? What a cumulative frequency does is it's kind of like your GPA, right? So cumulative GPA means go from this semester all the way back to the very beginning. So if you're in your very first semester, whatever your GPA is in your first semester, that's also your cumulative GPA. That's the only semester that you have. So for the very first bin, the cumulative frequency will always just be the same as its frequency, right? Whatever the frequency was, because there's no bin below it, right? There's no semester before it. Okay? However, when I start looking at the next bin, my cumulative frequency is going to be how many observations are in this bin, but also in every bin below it, right? So here I've got 7 is the frequency of this bin, plus the frequency of the bin below it would be what? 12? Or another way of thinking about cumulative frequencies is, what I'm really saying is how many observations are less than the maximum of this bin, right? How many observations are between 10 and 20, and between, or sorry, not and, or between 0 and 10, right? I'm adding up the frequencies of every bin below it. So I can kind of think about this as really representing the cumulative frequency is telling me this is the number of observations below 20. And then for the next bin, the cumulative frequency is take the frequency of this bin plus the frequency of every bin below it. So 3 plus 7 plus 5, I'll have a cumulative frequency of 15. Or the number of observations that are less than 30 here, well, that's everything that we had drawn up here. So 7 plus 5 plus 3 would be 15. Okay? The cumulative frequency is telling you the number of observations that would be in this bin or any bin below it. Okay? Any questions there? So once I get to the highest bin, let's say this is the highest bin. What does the cumulative frequency of the very last or the highest bin represent? It should represent. So let's say I was doing income and I said, the last bin was 250,000 or greater. The cumulative frequency of that last bin should be counting every single person, right? Because we either are in the highest income category or you're in something below it. So when I get to that cumulative frequency of the last bin, it should represent my total number of observations, right? Because I should have counted up every observation in only one of these bins. And then when I get to that very last bin, it's adding up every bin below it. So it's covering all of the data. So the total number of observations will be the cumulative frequency for that very last bin, which means my cumulative percent frequency for that last bin should be what? If it's every single observation, cumulative percent frequency would be 100%, right? I've counted every observation. It's 100% of the data, which means the cumulative relative frequency would be what? Not 100. That's percentages. Relative frequencies represent proportions, so 1. Exactly. So that's the idea of cumulative frequencies. We can do cumulative relative, just regular, or cumulative percent frequencies. And I just wanted to kind of do a little bit more review on that because I didn't love my explanation in the video. I wasn't like super sick, but my brain was definitely not 100% acuity last week. So I want to make sure I went through that again. So before start working on that Connect and Excel assignment, we won't have an online quiz today, but there will be one after class Wednesday. That's due before we start class on Friday. I want you to start working on those homeworks. We'll do measures of dispersion on Wednesday. Try to stay warm and safe out there, and I'll see you guys on Wednesday.